Having introduced the motivations for the nuclear shell model in the previous lecture, we will look at important questions that are going to lead to the quantization observed within the nuclear shell model. So, we had mentioned that for quantizing electrons, the potential that needs to be used is clear. That is, the confining potential is offered by the positive charge of the nucleus. In the case of atoms, it is spherically symmetric, and there are also repulsive interaction between the electrons. However, it is not clear what is the potential within the nucleus because the nature of strong interactions is much more complicated. All we need in hindsight is that if the confining potential is of some form, the quantization is not too sensitive to the nature of the confining potential. So one of the simplest confining potential that can be used for obtaining the energy levels for the nucleons is this. It is something like a particle in a box uh, model, right? So you would have seen in your first introduction to quantum chemistry or quantum mechanics, you would have heard one of the model problems of particle in a box, right? The particle is confined in a box. So this is pretty much like that. So this is a very large negative potential which confines the particle, and the particles will not exist beyond a particular point because the potential energy is much higher in that region. So this is one of the commonly used potential for modeling the properties of the nucleus. Another important potential is the potential of harmonic oscillator. From your high school, you would have seen this uh, kind of potential. This is the harmonic oscillator. This has certain advantage over this. But what is important to understand is the energy levels or the general features of the energy levels, not the details, but the general features are not too sensitive to the nature of confining potential. So, uh, so any one of these potentials um, is effective in giving you the right qualitative features that can explain many of the observations, like the magic numbers. We will see. So if you have this harmonic oscillator potential, if you have a three-dimensional harmonic oscillators, uh, you have three different numbers corresponding to three different dimensions. This is indicative of the 0 point energy that is seen in the quantization of harmonic oscillator potential. What is critical to observe is that your energy levels are specified by the n quantum number. As you as we elaborated in previous lectures, quantum numbers indicate some conserved quantity, right? So here, energy is a conserved quantity, and it is specified by this quantum number n. So we will elaborate on this n, capital N, shortly. So n, this formula is condensed into this. So n is indicative of these three, n1, n2, n3. You will also see that n is represented in this manner. 2n minus 1 plus L. We'll see what these things mean. L is the angular momentum quantum number. Again, this you might have heard from your high school, especially when you looked at the Aufbau principle, right? Aufbau building up principle, which helped in rationalizing the periodic table. You had this s orbital, p orbital, d orbital, and so on. Those are all indicative of the angular momentum. and it is s orbital corresponds to L equal to 0, p orbital corresponds to L equal to 1, and so on, right? So in classical mechanics, if you have a square of the angular momentum, just taking a square root will give you the angular momentum. However, that is not the case in quantum mechanics due to certain principles, especially certain principles involving uncertainty principles. So in quantum mechanics, the formula for obtaining the angular momentum is the square root of L times L plus 1. Uh, this is h by 2 pi h bar. So uh, it is not just the square root of L squared. It is the L times L plus 1 that gives you the angular momentum. So if this is not clear, you should take a class in quantum uh, chemistry or quantum mechanics, but that is not too critical for what we are going to be discussing in the rest of the course. In the rest of the course, we will use some uh, results obtained from quantum mechanics of the nucleus and see the consequence. That's the so within the scope of this class, detailed knowledge of quantum mechanics is not required. But you want to understand this in greater detail, I encourage you to take a class, especially in quantum chemistry, because I feel the many body nature of nucleons is more closer to many body nature of the electrons. Okay, so many of the models that we'll be using is more closer to the methods that are elaborated within quantum chemistry. So I would encourage you to take a class in quantum chemistry to understand many of these things. So let's move on in any case. So we also had some rules in uh, the electronic structure of atoms, the values that L can take in your previous classes, let's say even from your high school, you would have heard that L can take the value up to n minus 1, right? So here it's slightly different. L can take the values of n minus 2, n minus 4, and so on till it gets to 0 or 1. N is called the radial quantum number and can take the value of 1, 2, 3, and so on. So let us, this looks similar to what you have seen uh, to describe electrons in an atom, but it's different also. In some features, it's similar, some features is not similar. So let's try to contrast. Okay, so what you've seen when you say atomic, I mean electrons in an atom. So both electrons are nucleons within the atom, but you would have already seen something about electrons in the atom. So when you say 3s orbital in atoms, in this we are referring to the wave function of the electron, right? So when you say that, we mean L equal to 0 corresponding to s orbital and n equal to 3 corresponding to the principal quantum number 3. In the nucleus, when we talk about the quantization of nucleon structure, we when we refer to 3s, some things are similar. Again, corresponds to L equal to 0 and small n equal to 3. However, we also specified a formula for n, capital N. This is going to be pretty important because this n is what specifies the energy level of the nucleon. So if you implement the formula mentioned in the previous slide, so n corresponds to 4. So why do we have this capital N? So the electrons in an atom or the electrons in a solid and liquid, they feel the Coulomb potential. For the Coulomb potential, if Coulomb potential is the only determinant for quantization, N is enough to specify the energy. So N is a central determinant of energy. So you would have heard in hydrogen or hydrogen-like atoms, that is, what are hydrogen-like atoms? Hydrogen has one electron. Singly ionized helium has one electron. So it can be, it is a hydrogen-like atom. So hydrogen, helium, lithium, right? So if you have doubly ionized lithium, that is Li2 plus, is also like hydrogen. For all the hydrogen or hydrogen-like atoms, the energy is completely specified by the principal or the small n quantum number. Even for, let's say, atoms beyond, let's say, 2 electrons, 3 electrons, and so on, to the first order, the energy is specified by n. It may have contributions from other quantum numbers, but to the first order, that is the dominant contribution, is specified by the principal quantum number n. Okay, so if all these things are not clear to you, you should take a class in quantum chemistry or quantum physics or atomic physics to understand all these things. But again, I'm stressing that detailed understanding of quantum chemistry or quantum physics is not required for this course. But what is important to register is in Coulomb potential, N is a central determinant of energy. In contrast to Coulomb potential, the nucleons experience the strong nuclear interactions. So energy is not determined only by N. There are other determinants we'll see. Both capital, the capital N is the central determinant of the energy, which in turn depends upon both L and small n. So this is the formula that we had shown for N. So this capital N is going to specify the energy levels for nucleon structure. This in turn depends upon small n and L. So we have the occupancy for each L, like you had an occupancy in electronic structure. So for L equal to 0, which specify S states, the occupancy is 2 given by this formula. When we say L equal to 1, that specifies the P state. The occupancy is 6 by this formula. So this is the formula that provides the occupancy for different L quantum number. So this state can take 2 nucleons. This state can take 6 nucleons. This state can take 10 nucleons, and so on. And then for different possible n's, based on this formula, you can have different possible n, that is small n, and L quantum number. So when n equal to 0, you can have, you cannot have, you can only have S equal S states, that is L equal to 0, right? All right. So n has to, okay, so this is the state that is possible. When n equal to 1, so if you put this in here, you may have p states also possible. So the p states will have an occupancy of 6, as shown from here. So the cumulative occupancy becomes 8. So if you have n equal to 2, you may have both S and D states. The cumulative occupancy is 20, and so on. We are referring to this book because for many reasons, it's freely available for download. You can read from this, and some of the aspects of nuclear science and engineering relevant to India is also mentioned here. But it has some typos and so on. For example, this is not right in this, but it can be corrected with some reading. But This is not too important. What is important to note is the following. So we had already mentioned the energy levels are specified by N. When N changes, there is an energy gap. So that is the most important thing. We will see, we'll provide a general structure for energy levels. We will not derive that energy structure. So only I'm not too bothered about all these things, because we'll be presenting the energy structure and we'll be using that energy structure without deriving that energy structure from basic quantum chemistry or quantum mechanical principles. So in the next lecture, we will present the energy levels that are going to be utilized for filling the nucleons. So in your high school, you would have seen the Aufbau's building up principle, right? So the question we are trying to address is that for electrons, there is this Aufbau building up principle. For nucleons, what is the corresponding energy levels, which is like a ladder, right? There are low energy levels and high energy levels. So as the nucleon number increases, we first fill the low energy level and then the higher energy levels. So what is that energy level? That will be presented in the next lecture. You will also introduce, we will also introduce something called spin orbit interactions that are very critical for explaining the properties of nucleus. All these things have consequence for rationalizing the isomers that you see within the nucleus. All these things will be discussed in the next lecture. Thank you.